Modern artificial intelligence systems generate highly functional code, draft complex financial strategies, and synthesize original art on command. But the broad concept of AI, defined as any machine executing a task in a way that mimics human intelligence, actually dates back to the 1950s, starting with Alan Turing's question, can machines think? For decades, the answer was early expert systems. Programmers manually hard-coded millions of rigid if-then rules to teach the machine how to behave. These systems faced a severe limitation. If a scenario didn't perfectly match one of those pre-written rules, the entire program failed. Because they relied entirely on explicit instructions, early AI was fragile. For a machine to exhibit actual intelligence, it needed a way to learn from data on its own, rather than waiting for a rule to tell it what to do. In the 1990s, computer scientists shifted their approach. Instead of writing endless logical rules, they started feeding computers large amounts of statistical data so the machines could figure out the patterns for themselves. This is machine learning. It is a subset of AI that uses data-driven algorithms to organize the data and make predictions, removing the need for human programming. Around 2012, an explosion in GPU processing power and massive internet-scale datasets accelerated the shift toward deep learning. Deep learning uses multi-layered neural networks modeled loosely on the human brain to solve complex, nonlinear problems. Processing raw inputs like speech or pixels requires massive mathematical calculations. This leap in computational power allowed models to move past spreadsheets and start processing the chaotic data of human vision and audio. For decades, both machine learning and deep learning were primarily discriminative. They were designed to analyze and categorize data that already existed. This chart shows how discriminative AI works. It learns the mathematical boundary that splits two categories of data, like predicting whether an incoming email is spam or safe. In 2020s, foundation models trained on the public internet introduced generative AI. Instead of finding boundaries between points, it learns the underlying mathematical distribution. By calculating probabilities, it fills the space with entirely new synthetic data points. A modern model synthesizes a completely new sequence of words on the fly based on the patterns it learned during training. This shift from analysis to generation is actively rolling out across global enterprise infrastructure. In healthcare, these models automate medical imaging analysis and help synthesize chemical compounds for drug discoveries. In software engineering, they operate as AI care programmers, generating automated test cases and migrating decades-old legacy code into modern languages. Because these tools are becoming foundational to how businesses operate, industries are facing a shortage of technical builders who know how to deploy them. The rise of the AI engineer follows the demand for professionals who can integrate foundation models directly into existing business workflows. Doing this requires a specific tool stack: Python for its library ecosystem, Visual Studio Code as the primary environment, and Jupyter Notebooks for testing code cell by cell. They also use new architectural methods like retrieval-augmented generation, or RAG pipelines, to securely deploy these models alongside private company data. The core nature of software development has shifted. You are no longer writing strict rules to command computers what to do. You are architecting environments that guide them on how to create.